You may recognize this equation as the equation of a circle. You learned this last year. But my question right now is this. How do you differentiate that? Well, you could look at this and try to express or put this in terms of y equals something, but you will get something like this, and this is not even a function, all right? For each value of x, you would have two values of y. You could still try to differentiate that, but it will be too complex. There is another way, much simpler way of differentiating this in terms of x. And the good news is that you already know all the tools required to figure this out, and that's what we're going to do. Let's differentiate this by differentiating what you have on the left-hand side of the equal and what you have on the right-hand side of the equal. That's what I did over here. Okay? So here you have the sum of two functions, so we may separate these two. And if you differentiate one in terms of x, that's just going to be 0. Differentiating this is very simple. Dx squared by dx is just 2x. What about that? You are differentiating y squared in terms of x. And you don't know how to do that. But you know one rule from last year that will allow you to get somewhere. Don't forget and don't lose track of what you want. You want to differentiate an expression. So at the end, you want to have an expression that looks like this. dy by dx equals something. All right? You want an expression for all possible gradients of y in terms of x. So dy by dx equals something. That's your ultimate goal. All right? Keep that in mind. So we can use the chain rule over here to get just that. Because dy squared by dx is the same as writing dy squared by dy times dy by dx. Right? So just do it. What is the advantage of that? Is that now you are able to differentiate this in terms of y. Dy squared by dy is just 2y. Right? So you have the 2x that you had before, plus 2y times dy by dx equals 0. Don't forget what you want. You want an expression for dy by dx. And you already have dy by dx over there. So let's just isolate this in one side of the equation. Send this to the other side. Send this also to the other side. And here you have it. Dy by dx equals 2x minus 2x over 2y. Or just minus x over y. And this is what? This is an expression that allows you to determine the gradient of the function y in terms of x, just knowing the coordinates of y and x. So this allows you to determine the gradient of the circle at any of its points. As long as you know that the point belongs to the circle, you can plug in the coordinates over here and you get the gradient on that point. For example, the gradient of the circle on these points, all of them belong to the circle, are these. You just substitute the x and the y coordinate over here, and you get the gradients. For these points in particular, you have here the gradients. This is the circle to begin with. The center is 0, 0, the radius is 1. And here are the gradients on these points over here. Okay? This is called implicit differentiation, and the functions that are not defined in a traditional way, y equals something in terms of x, these are called implicit functions. Let's see other examples. This one over here, okay? You want to differentiate that. So again, differentiate the left-hand side, differentiate the right-hand side. This is a sum of two smaller functions, so you'll just have dy cubed by dx and dxy by dx equals 0. You just differentiated a constant, and that is 0. Again, you are differentiating a function of y in terms of x. So here you'll have to apply the chain rule as we did before. So this is dy cubed by dy times dy dx. And this is what you want. You want an expression that has dy dx. Don't forget. What about here? Here we have a mixture of two things, of two different unknowns, the x and the y. So what do? Just apply there the product rule. What is this? This is going to be just x dy by dx plus y dx by dx. All right? And what is dx by dx? It's just 1, so this is just y. And over here, what do? Let's look at this one first. So dy cubed by dy is 3i squared dy dx. All right? And here you just have x dy dx. So now you have two expressions that have the term dy by dx in it. So you have to factorize the dy by dx, leaving inside the brackets the 3y squared plus x. I just sent the y to the other side, became minus y. So dy by dx is going to be minus y over this stuff. So imagine that I want to know the gradient on point 1, 1. Go over here, substitute x by 1 and y by 1, and the gradient is going to be minus 1/4. Okay? Again, implicit differentiation involves using the chain rule and the product rule, or the quotient rule, or any other rule that you've learned so far, by that matter, in order to have expressions in terms of dy by dx. Another example. This one over here. Do the same thing. Differentiate the derivative of this in terms of x equals the derivative of this in terms of x. And now let's just apply the rules that you've learned. These are separated. Here you may apply the product rule. I just sent a 3 to the outside. You can also apply the product rule with a 3. But every time you have a constant, the constant can just be placed outside. You already know that. So you apply basically just to the x squared and the y cubed. If I differentiate this, it's already in terms of x, so this is just 3x squared. Here I have to apply the chain rule. Here I'll just leave the 3 outside, and I will have to apply the product rule to these two. Okay, just like I did before. Going back where we were, this is just 3y squared dy by dx equals 3. This is just 2x times the y cubed. This is what? You have now the dy cubed by dx, so I have to apply here again the chain rule. And this is going to be 3y squared. I didn't change anything until here. All right. So you have now, I'm going to multiply now this 3 to get rid of the brackets. And I have now two expressions with dy dx. I have to combine them. So I send this to, no, I send that to that side and this to this side, and I swap position. That's what I did. Factorize the dy by dx. Cut things that may be cut. And eventually, this is the expression that I get for the dy by dx. I think this is as complicated as it gets. And you just did several times the rules that we were following until now, which are what? Applying the chain rule, applying the product rule, apply the chain rule again, and that's it. I had to apply the chain rule twice, I think. Yeah, and then combine things that need to be combined until you get an expression for dy by dx. That's what you get. One last example. I think it's the last one. Yes, it is. Find the coordinates and nature of the stationary points of sine of x plus sine of y equals 1. This is also an implicit function. It is defined in terms of x and y in the same expression. All right? So you just have to follow the same rule. You are given points that belong to the curve, so you know that these points belong to the curve. This is going to be useful at the end, as we're going to see. But right now, it's just time to differentiate that. So again, differentiate the left-hand side in terms of x, differentiate the right-hand side in terms of x. This is going to be 0. This is going to be this sine of x by dx plus this sine of y by dx. This, you already know, is the cosine of x. Here you have to apply the chain rule. So it's the sine of y by dy times dy by dx. So the cosine of x plus, this is again the cosine of y now, dy by dx. So dy by dx is going to be minus cosine of x over cosine of y. You want the stationary points. So for you to get the stationary points, you know this since last year, you have to equal the expression for the derivatives to 0. That's what I did over here. In order for this to be 0, it only happens when the cosine of x equals 0. So the x equals pi over 2. You want the coordinate of the stationary point. Right now you only have the x coordinate, so plug this on the equation. All right, that's what I did over here, and solve it for y, and you have y equals pi. So, oh sorry, you have y equals 0 or y equals pi. So the coordinates of the stationary point is going to be pi over 2, 0, and pi over 2, pi. But you also need to get, besides the coordinates, you need to get the nature. What does that mean? It means that you need to know if it is a maxima or a minima. You could differentiate it again and get the double derivative, but I'm going to use instead these points over here, because I can check the monotony of the function on points just before and after the stationary points. I just plotted here, in the beginning, I just plotted here the stationary points, all right, the P and the Q. And now I just plotted here the coordinates of these points over here. If you look at it, you just have pi over 6 and 5 pi over 6. So for the point P, P was the pi over 2, 0. I can check the monotony of 2 points, one before and one after. This will be the pi over 6, pi over 6, and 5 pi over 6, pi over 6. All right? So what do I do? This over here. I substitute the values on the expression. Where is it? On this one over here. And I'll see that for this one, I'm going to get a negative value. And for this one, I'm going to get a positive value. Negative, positive, so this is a minimum. Do the same thing for point Q, using these 2 points. Substitute these coordinates on the expression. I get minus 1. I'm sorry, I think I did. Something's wrong over here. Pi over 6, 5 pi. Okay, so this is 1. And that is 5 pi over 6. 5 pi over 6 is minus 1. Okay, so this is a maximum. So a little while ago, I might have made a mistake. This is pi over 6. Pi over 6 is minus 1, correct? This is pi over 6. 5 pi over 6. Pi over 6. And this is... there's a mistake. This should be plus 1, okay? So this is a minimum, okay? This may be plus 1. So here you have 3 examples that use implicit differentiation to calculate stuff, or the same type of stuff that you were calculating already last year, like maximum, minimum, points of inflection, etc.